Okay, so we will be writing a program to understand how an array behaves in a C program. We will look at how data is stored as a payload within the array, how it is accessed, either using an index or a pointer. So these will be the objectives of this exercise. Prior to that, I would like to visually show what an array might look like in memory and how we would label any location within the array depending on the data type that you declare the array to belong to. For example, let's say you declared an array of integers. Okay? So in memory, let's look at memory itself. Let's say memory is composed of a number of bytes. So I'm going to stack them like a building here. So we have a bunch of bytes. Okay, bytes is 8 bits. Okay. And this is RAM, or random access memory, but it's allocated for your program, right? So it's the stack assigned for the function that you're running. Okay, so let's say you did something like this. Int my array three, and then you put a semicolon. So what you've done here is you technically wanted 3 locations in which to store data and or your payload. So your payloads are going to go over here, and over here. The advantage of this, however, this is a data structure, is that the location where the first payload is, right, will be here. The next one will be in the next consecutive memory address allocated for an integer. Now, in other words, what does that mean? Now, remember, an integer takes up, in our case, 4 bytes in memory. Okay, so for each integer, we need 4 bytes. So this would be 4 byte long, 4 byte long, 4 byte long, right? Okay, so we have 12 bytes to represent this array, or to actually have a space to store 3 numbers, right? And then we will be able to sequentially access it one way or the other, or randomly, which means we can pick any of these and access the data. So in terms of memory, let's say the computer allocated the first memory location right here, right? And so what's going to happen is, remember, this is a stack. So what it's going to do, it's going to count 1, 2, 3, 4. That would be your first element. The next element will be right after it. 1, 2, 3, 4, and that would be right here. And the next element will be right here. 1, 2, 3, 4, and that would be right here. Okay? So this one will be this one in memory. This one will be this one. And this one right here will be this one. Notice that each one takes 4 bytes. Okay? So 1, 2, 3, 4 bytes to store data. Okay. So now, how do you access any of these bytes and put data in them? Right? So there are several ways to do this. Now, by declaring your array here, what you've done here is you've told it what is the size, total size for your array. So it automatically calculates how many bytes total you need. That's, I hope, is understood by now. Okay. So we know it's 12 bytes, right? 4 times 3. Okay, since each integer will take up, or each payload will need 4 bytes to reside in. Okay, so how do we access them? So the way to access it, you could use what we call an index. Okay, it resembles what you did here, except this would be index 0, 1, and 2. So you have 3 elements starting at page basically 0, then page 1, and then page 2 to access it. So if you're doing an index access, you could say something like this. My array at, let's say, 1 will be equal to 56. So what just happened? Well, let's go to memory here. This would be at index 0. This would be at index 1. And obviously this would be at index 2. So what happened is that you're going to use up all of this space from here to here to store 56 as an integer. Now, 56 does not need all these 4 bytes to store data in it. It can be stored within 1 byte, but it will be padded. Okay? So the reason you have 4 bytes for an integer is so you can express much larger numbers than, say, 56. So it gives you a lot more flexibility in terms of the integer size you can store, the whole numbers you can store within a regular integer. Now, are there other integer or specialized integer that can handle 8 bytes? Yes, that's called a long int. So had I said long int my array, right? So we would have to have doubled the size of memory allocation we would need for this array. Okay, so how would I display? So this would be for the assignment. This is how you would assign a value at a specific location. Notice I did it randomly. I just picked 1, right? Eventually you could do it sequentially, which means you could have picked 0, then 1, then 2, or in reverse, 2, 1, and 0, right? That would have been a sequential access. Random means just pick an index that is valid, right? In our case, the valid indices will be 0 through 2. Okay? So how would I display this? How would I display what's in here? Well, simply if we're in C, then a printf statement will do just fine. Then a %d here, okay, comma, and then my array. You would handle it just like a variable. Make sure you put 1 here, and there you go. So whatever is in here will be displayed in this placeholder right here. So this allows you to assign. It happens to be at compile time. Now, let's say we want to assign at runtime, which means while the program is running. Maybe for that, you will use a scanf function, right? And then that would be a %d since you're entering a decimal number. Now, notice what I'm going to do here. And my array. And let's say we go to 0. So what happens here when the program runs, so this is a runtime assignment, which means it's going to wait until the program is running to actually assign a value at this location. And notice the %, here, which means use the address to store this data in. So let's say this program is running. Here's your terminal, right? And you have a prompt here waiting for you to enter a number. Let's say I entered 19 and I hit enter, right? Okay, so as soon as you did that, then 19 will get stored right here. So from here to here, and obviously 19 is a small number to be stored in 4 bytes, so it will be padded, okay? So you'll get the equivalent 19 in binary, and the rest of it will be padded to fill in all 4 bytes. So that's how it would be done at runtime. This here is what we call compile time. So that means you wrote this in your code. In your source code, you said my array 1 equal 56. This one here you cannot predict until you run the program. Then while I was on the terminal, I entered 19. But notice the difference in the assignment. Here you treat it just like a variable, so you same thing here, except you have to be really, really careful. Notice I'm highlighting this, that it is at a certain memory location. This scanf function wants a reference. It wants an address as its second parameter. Notice the comma here. There are 2 parameters. What kind of data and where? Okay, so that is how scanf works. Okay, so after that, if you do a printf, if you have a printf statement right after this of %d, and more specifically, notice here you don't type the n% here, right? If you did, you're going to get an address. My array 0, right here, semicolon. Now what's going to happen is as soon as you're finished entering 19, 19 will display on your terminal. Okay? Because you just had a printf or a print statement right after your scanf. And it will pull out the data in my array. Now, what if you made a mistake and did this? Printf. Or it could be not, it may not be a mistake. Maybe that's your intention. You did this. And percent my array 0. So what would that yield? Well, that will yield simply, it will print an address. You may get something like this, 2837, right? So this looks like an address. So what it means is the address right here of the first byte is 2837. The next byte is 2838. The next byte is 2839. The next byte is 2840, which means the next data member will be at 2841. So if you did this, printf %d and percent my array 1 this time, what you would get in the terminal is 2841, right? So there's an offset of 4 bytes between them. Okay, so that's going to be extremely important to understand. That means, okay, as you go from one element to the next one, you're moving by 4 bytes. Well, that's going to be important if you want to access now the array using a pointer rather than an index. So to do that, let's go over here on the side here. Let's say this time we create a pointer, and let's do an int asterisk my PTR. Now, this pointer is somewhere in memory right here. It takes 4 bytes as well. 1, 2, 3, 4. Let's say it's right here. And this is the space reserved for my PTR. So it is still a variable, except I haven't put anything in here, right? Now, if I do this, so this here, you just simply declared a pointer. You didn't do anything with it. Now let's do something with it. And I say something like this, my PTR equal the and percent my array 0. Aha. So what did you just do here? Well, in that case, you took this value, 2837, and you stored it right here, 2837, and you used up all your 4 bytes as, so what you have stored technically is a reference. Aha. So if that's the case, then if it's a reference, I can dereference. Yeah. Now, if you did something like this, printf, and a %d here, for example, and you want to dereference the pointer. Dereferencing the pointer, you type an asterisk in front of it, my PTR. What is this going to do? It's going to go to this location, 2837, look at the payload, and it will print for you a 19 on the screen. Now, what if you forgot to do star PTR? What if you did this? Printf %d, and you didn't put a star, but you just simply went ahead and printed my PTR. What would happen? Well, it will print 2837 because that is what is stored at that location. Now, what if you decided to say, okay, well, how about I do this? I'm experimenting, right? So let's see what happens if you do this. And let's say you do %d and percent my PTR. Now this gets interesting. Not very useful, but it's okay. So if you do that, well, what you're going to be doing is print the address or where your pointer is. right? So let's say your pointer somewhere in memory was at 2755. What's what you're going to get is 2755. That's what you're going to get right here. You're simply printing the address of the pointer. Okay, that's for the system to keep track of. You're interested in what is your pointer pointing at, which is this part. That is my interest. Okay, I want to make sure that I assign my pointer to the first address of the array, for example, or the second address, or what have you. So that is all in all what we're going to be exploring code-wise, and make sure that we understand this behavior and how to access the array at compile time, at runtime, using a pointer, and get comfortable with this. So one thing I'm not going to do is do arrays or access arrays using loops. That will be for another session after I introduce you to loops and how they work, and which are very useful when you have data structures like arrays. So on this, I will stop on this part here. This will be part 1. Part 2 of how we're going to handle arrays, we're going to start writing code in C. Thank you.